Testing 1, 2. Welcome to the class. Denise, is that right? And Kutso.
Turn the volume up as loud as you can.
Hallo Liesel.
Hallo Charles, hoe gaan het?
Dit gaan lekker, dankie. Met julle? Het julle nou al winter?
Ja, ons vries.
Wow, okay. Right.
Ja, die oggend is so lieflike 4 grade.
O nee, okay, net sal nooit 4 by my wees nie. Ja, ons winter het gister begin.
Lieflik.
Ja.
En wat kan voor dit die dag?
Ek dink is 12 of 13. Ja, ons is softies die kant wat koue betref.
Nee, dit is reg. Goed, so is hier, ek het vir hom daai goed gestuur, die beplanning vir die kwartaal, ek het die foto vir hom gegee.
Okay, ek gaan net gaan met hulle gesels. Okay, welcome to the class, Kutso. Hi Benice, are you well?
Hello.
Kutso. Are you with us, Benice?
Yes, hello.
If you can just slightly speak up, I can't really hear you.
Hello.
Hi. Okay, I did forward something that looks like this, only the planning. So I've just looked at the workload, looked at the planning. So basically we are on the 6th of May today, so we should be doing Doppler effect and also energy on work, questions on work and energy. Next week, we'll be looking at rate of chemical reactions and then any questions on Newton that you have, or we can say any questions basically on anything. Okay, in other words, what I want you to do for next week, you need to finish off rate of chemical reactions if you can. That will just speed up the process. So it's better if you finish the section and then I explain questions or explain some examples on that question, because then you've on that chapter, because then you've done the work already and you've done the theory. Otherwise, I have to waste time doing the theory, which I don't want. This is the only way we're going to go through it. The only thing I want you to do, I want you to look at these dates coming and then tell me if there's one of those dates that you can't make because of other exams, and also if you can't make this time slot because of other exams, then we'll just move it. Okay, I think, Benice, you've sent me something, but I've forgotten about it. I'm not sure. Anyway, look at those slots, and then you just let me know, okay, fine. Say, for instance, June the 3rd, you can't do this time because you're writing an exam or an oral or whatever. These are your two exam dates. Right, so they're not lessons, they're dates. We can work in extra time if we have to before that. So I've just slotted in all the, I'm not sure, all of them do look, yeah, they're all on Thursday. So just look at it and get back to me. Okay, today we're going to look at Doppler, and we're also going to do work energy questions or any other questions that you have. So Benice, you sent me something, we'll do that. Kutso, do you have any specific questions?
This is exactly what I wanted to go through today, the Doppler effect.
Okay,
so
look at the Doppler effect. But first we're going to do work energy questions because that's the work that we finished last week. I think this is the question. Is this the one you wanted, Benice?
Yes.
Okay, right. Now, a box of a mass of 300 kilograms slides along the surface of a rough bank. So that means there is friction. If you read a rough surface lies along the surface of a rough bank, then you already know that there is going to be friction. So I'm just going to make an if there, no, just to indicate to myself there is friction involved. Okay, the angle is 20 degrees to the horizontal. It passes x at 2 meters per second, and then it reaches the end of the slope at 5 meters per second. Right, the distance is 12 meters. Okay, state the work energy theorem that you have to learn. Okay, you are going to get it. Calculate the magnitude of the net force acting on the box as it was sliding down the bank. Okay, there's possibly two ways of doing it. In general, when we do energy and work, or work and energy, they don't want you to use equations of motion. But they didn't state anything here, so we could use equations of motion, but I'm just going to leave that for now and just use energy principles. Remember, if they say use energy principles to calculate whatever, then you're not allowed to use equations of motion. Very important. You'll get 0. So if I say, okay, fine, I'm just going to do the acceleration, and I'm going to use, I've got initial velocity, I've got final velocity, I've got displacement, I don't have time. In other words, I can use this equation. Vf squared equals Vi squared plus 2a delta x. This is to calculate the acceleration, because then I can use Newton F net equals ma to calculate the net force. I'm allowed to do this now, but if they told me use energy principles to do it, then your teacher will just do a red line through your whole sum and you'll get 0 because you didn't use energy principles. You used equations of motion. So I don't really want to use this, because normally they should state use energy principles. So the question is, which equation are we going to use? The answer is you can use V net or you can use VNC. They both get the same answer, or you can solve all of the sums by using any one of those two equations. Unless they've stated use the work energy theorem, then you're only allowed to use that one. Then you're not allowed to use VNC. You will also get 0 again if you esse VNC. Okay, so let's see how far we can get with that equation. So the net V net equals the change in kinetic energy. Good. Before I do that, I just want to draw a quick diagram of forces. So I have normal, I have friction, I have the force of gravity that's parallel to the surface, and I have the force of gravity that's perpendicular to the surface. So my net work is the work done by friction plus the work done by the parallel force, and that will give me the change in kinetic energy. Okay, you could have gone and worked out the net force first. It's a bit of a problem because I don't have the friction. Okay, or because I ask for the magnitude of the net force, I can replace these two with just saying, okay, V net is F net delta X cos. Okay, let's just get more space there. I don't have to break up that component. I can just do F net delta X cos theta, because V net is F net delta X. Okay, cool. So the change in kinetic energy is half times the mass times the final velocity square minus the initial velocity square. And the net force I don't have, because that's what they're asking, F net over a distance of 12 meters. And the net force is downwards and the movement is downwards, so that will be cos 0 degrees. Half of the mass, 300 kilograms. The final velocity is 5 and the initial velocity is 2, I think, yeah. And that is just going to be 12 times F net. And that is just calculator work. Type that into your calculator. So F net is 262.5 Newton. Downslope. Got it? So I'm so used to breaking up V net into all its components, that I did that immediately without just reading the question. If I read the question, then we would have just worked with F net. You could have used normal, to test your answer, you can use the equations of motion. Right. Calculate the magnitude of the frictional force acting on the box as it was sliding down the bank. Right. What are we going to do there? What would be the easiest way to do that? Let's give it some thought. What would you do to calculate the frictional force? What is the force of kinetic friction as it slides down the bank? Well, you can set up one of the equations. Okay, it's only 3 marks, so that's interesting. I would have thought it would be at least 4 marks. What would you do? Well, you can use this. F net equals what? The force, let's just call it friction. The force of friction upwards, so it's negative, plus the force G that's parallel. The net force is the sum of all the forces. So I'm using this diagram here, this forces diagram, free body diagram, to actually break up F net. Okay, cool. So F net was 262,5, negative the frictional force, and then FG parallel is mg sine alpha. Can you remember that? That's Newton, that's grade 11 stuff. So I have 262,5, that is the negative friction, plus the mass, times 9,8, sin 20. Right, so I'm going to take the frictional force to the left, and I'm going to do 300 times 9,8 sin 20 and minus it with 262,5. I have a small mistake, or a technical mistake. My technical mistake is this. It's not wrong, but technically it's wrong. I'm really actually not allowed to give the frictional force a sign at the beginning, because the sum must give it a sign. So I'm just going to leave that as positive. That's going to allow me to get a negative answer, and then I can get the direction from the negative answer. It's not a train smash, because you would have given your answer upslope anyway, or against movement. So it won't change your answer. It's just not the way they want you to write it. So I'm just going to write it exactly the way they want to. So if I do that, I get negative 743,04. So the frictional force is 743,04 Newton. Just confirm that.
Yeah. Yes.
Was there another way of doing it? Yes. This is why it's 3 marks. Because I thought just 3 marks is it's not enough marks. It should also be 5. Because you could have used this easy Newton method. Or if you didn't think about that, I'll give you a minute now to screenshot the sum. You can also have done this. VNC equals the change in kinetic energy plus the change in potential energy.
Potential energy.
Yes. Okay. Well, the thing is, the change in kinetic energy is basically, we can just steal it from the top part of the sum. You see there, that's the change in kinetic energy. So VNC is the work done by friction plus the work done by the normal force. And that is, okay, let's write out equation, half m Vf square minus Vi square plus the change in potential energy, which is the mass times gravitational acceleration, the final height minus the initial height. Okay, that we just have to fix or work out. Now, the this WF, I'm just going to leave. Otherwise, I don't have enough space. Plus 0. The work done by the normal force is always 0. This is half. I don't have to, I can just copy it there. Half times 300 times 5 square minus 2 square. Now, look at this. The mass is 300. Gravitation is 9,8. The final height is 0. And the initial height I don't have. I have to work that out. Well, it's not difficult. That's the height, and that angle is 20. So sin of 20 is opposite over hypotenuse. So height is 12 sin 20. Now I don't have enough space. So that is 12 sin 20. It looks exactly like the other sum, basically. All right. Now type that whole right-hand side in my calculator as is. Let's do that. I'm going a bit slow. Is it 30 or 20? I don't know why I've got, it's 20. I just wrote didn't write neat enough. That's 20, eh? So VF equals negative 8916,4106. This is joules. Remember, this is not the frictional force. This is the work done by the frictional force. So this is the frictional force times the distance times cos theta. You see, this is a longer sum. That's why I thought it was more marked. Okay, so I'm just going to divide it by 12, minus 12. So I've got here distance of 12 meters, cos 180. So I'm just going to divide that with 12. And then I get the same answer. The frictional force is 734,04 Newton upslope, or against the movement. So this is alternative method. That's an alternative way of doing it.
I have a question.
Yes.
With the fx cos theta, why is it 180?
Because the box is moving downwards and the frictional force is upwards, and the angle between those is 180 degrees. So that cos theta is always the angle between the force and movement. It's always a -1 or a +1 answer. Good, sir. So what I knew already was the frictional force must be negative. So that cos 180 must give a negative value.
All right.
Are you guys happy?
Yeah.
Right. Good. There will be other ways of doing it. They didn't limit us on how we could do it, but I'll stay away from equations of motion when I'm doing energy. You can use Newton, however. So that's why we could use this blue part here, because Newton is part of your energy equations. Newton falls under or with energy, but equations of motion doesn't. Right. Look, I'm going to be honest with you. Your workload is too much for the June exam. This is a lot of work, eh? It's going to be very tough. Okay, let's look at the Doppler. Have you looked at it, Kutso? Doppler effect at all?
Yes.
Okay.
Yeah.
I don't need to explain something, do I?
I would just like you to go through it just to see if I'm sure about what I'm doing.
There's like a police car. It's got like a siren on top. Let's make it there. All right. Now this police car is standing still. The velocity is 0. I'm going to put the siren on. So the sound waves are going to do this. They're going to go over the car. So whatever, if you stand in front of the car, or if you stand at the back of the car, the frequency you're going to hear is exactly the same. So why? Because the wavelength is exactly the same. Now, if this car starts moving towards the right, say for instance, what it basically does it catches the sound waves. It doesn't catch them. The sound waves are too fast, but the relative distance between the front and the back sound waves is actually visible, or in a spectrum you can actually measure it. Okay, so now this car is going to move to the right. So what it basically does, it rides away from the sound waves at the back and catches or comes closer to the sound waves at the front. So the wavelength at the front will be smaller than the wavelength at the back. Now, C equals F lambda. Okay, that means the frequency is indirectly proportional to the sound wave. So the higher let's say the bigger the sound, the lower the frequency, or the longer the wavelength, the lower the frequency. So I have a long wavelength at the back, so I'll have a low frequency. I have a small wavelength at the front, so I'll have a higher frequency. So someone at the front of the car will hear a higher frequency, someone at the back will hear a lower frequency. Right. So now, there's an equation they set up. This is just a reference so that you know the person that the car or the vehicle approaches, or the sound wave approaches, will have a higher frequency than the person that the sound wave or the vehicle leaves. So this is just your reference if you're doing it right or wrong. So we need to either calculate the speed of the car or the velocity, or you have to calculate the wavelength or the frequency. So there's your equations. That's your main equation. And this is just the speed of sound or light. In other words, sorry, that's the speed of light. Speed of sound will look like this. So we have sound or light. You can use Doppler effect for sound or light. And this is just that old equation if they want to calculate the frequency by using energy. And that's Planck's constant. Okay, but this is the main one you use. So let's copy that. Let's do example. This one looks easier. A truck approaches you at an unknown speed. Okay, cool. Let's draw the truck. There's the truck. It approaches you, there you are, with an unknown speed. The velocity is unknown. The sound of the truck's engine, okay, so in the engine, that's the source, it's a truck. The sound there has a frequency of 210 hertz. However, you hear that sound with a frequency of 220 hertz. Okay, now what's happening here? You're hearing it with a higher or lower frequency. You're hearing a higher frequency, so the truck is approaching you. Good, but that they said.
Hello?
Are you with us? Yes. Can you hear me, Benice?
Yes.
Okay, right. So I just want to get reference here that they are right. You're hearing a higher frequency than the frequency of the source. So the truck is approaching you. Calculate the speed of the truck. Okay, let's get that equation. I'm going to do this one example and then a harder one. Okay, so FL is the frequency at the listener. So this is FL. Fs is the frequency at the source. So that's the frequency of the source. Here we go. So the frequency at the listener is 220 hertz. Now, F there is what? Is either the speed of sound or the speed of light. Now they should give you that. The speed of sound is 340 over 340. And then plus minus, I'm going to answer those questions now. I'm just going to put the frequency of the listener in, of the source in, 210. Okay, now, what is the velocity of the listener? Well, the listener is not moving, so the velocity is 0. So you could just leave that out. You don't have to fill that in. Now, is the truck approaching you or going, it's approaching you? So now certain kids just remember, if it's approaching you, I think it's a minus at the bottom. And if it's leaving you, it's a plus at the bottom. I don't know. I don't learn stuff off by heart. I figure it out. Okay. To move from 210 to 220, I have to multiply it with a higher number on top and a lower number at the bottom. Do you agree? If you take 10 equals some fraction times, let's say 5, I have to have a higher value on top and a lower value at the bottom to convert 5 to 10. So I've got 340 at the top. I have to get a lower value at the bottom. So to get a lower value at the bottom, I'm just going to have a negative at the bottom. And that's the velocity of the vehicle, which we don't have. And the rest you can just calculate. If you have a cool calculator, you calculate, you put the equation in the calculator solves it for you. Otherwise, you have to divide the 210 under the 220. And then you have 340 over 340 minus VS. Okay, cool. I want to see if you can calculate that. Okay, let me use my calculator, see what it does. Everyone quickly do that calculation. We're all going to be faster than mine because I have to put like an X in. Who does have that? Does anyone have that silver calculator?
No.
Because I just typed that equation in, just like it, like that. I just typed that in. My calculator immediately gives me no, immediately. It takes about 10 seconds to give the answer. Oh, let's say 15 seconds now. I'm still thinking. So your calculator is going to be slightly quicker than mine. Answer, please. So what you're going to do, you're going to have 220 over 210, multiply 340 minus VS, and that will give you 340. And then you solve that calculator. I get 15,45 meters per second towards you. You get that? So you multiply that product and there, and then you just solve the equation. You're grade 12 now. You should be able to solve that equation. Speak to me, Kutsa.
Yes, 15,45.
You've got that, Kutsa?
See,
You have to multiply these two blue things first, and then the purple, the blue one with that one, and then you get fractions, and then you have to just solve it with your calculator.
Yeah, I got that already.
Good. Do you want to do another example?
Yeah.
Okay, let's go. This one is harder, I think. A source is moving at a constant velocity past a stationary observer. The frequency detected as the source approaches the observer is 2,600 hertz. The frequency detected as the source moves away from the observer is 1,750 hertz. I want you to quickly draw some drawing. Just make yourself some picture of what is happening. It's very important that you make a little drawing so that you get some visual reference to what you're doing. I'm giving it 15 seconds. Right, let's do. Okay, there's a, I don't know. Gonna draw a little car again. So there's one scenario. As the car approaches the listener, the frequency at the observer is 2,600 hertz. As the car leaves the observer or passes by the observer, the frequency is 1,700. Right. What do we have? We have the speed of the velocity of the speed of sound, and that's 340 meters per second. Okay, 6 marks for calculate the speed of the moving source. Can you see there's 2 scenarios? This is scenario 1, and this is scenario 2. So I'm going to set up 2 equations and solve them simultaneously. Okay. So for scenario 1, we have, let's do that. Put this equation here. You'll get it on a formula page. So the frequency at the listener is velocity of sound plus minus VL at the listener, velocity plus minus Vs, and that's the frequency at the source. So what do we have here? We have the frequency at the listener, because this guy here is listening to the sound, and this one is 2,600. We have the speed of sound, 350. The listener is not moving, so it's a 0 on top. And then we have 340. I'm going to do plus minus now. I'm not sure. The velocity of the vehicle of the source is what we want. I'm going to ask now if it's plus or minus. And then the frequency of the source we don't have. So we have 2 unknowns there. Okay, so the car is moving towards the person. And most students are just going to learn that's going to be a negative then. If something moves towards you, there's a negative at the bottom. Or you can just think, if this object is moving towards you, the frequency of the source must go to a higher value. So this frequency of the source must be lower than 2,600. So I have to multiply the frequency of the source with a higher value on top and a lower value at the bottom. So I have to minus at the bottom. I don't know. How do you remember this, Bernice? You just learn it.
Yeah.
You just learn that it's negative at the bottom if it's approaching you. I want to know from both of you how you're going to remember or reason if there's a negative or a positive.
When it's towards something or towards you, it's negative, and when it's away, it's positive.
Okay, that's if you have a good memory, then that's it. That's how you're going to remember it. It's the easiest way. Okay, scenario number 2. Now this, okay, let's write the equation first. Now this source is moving away from us. Okay, what do we have? We have the frequency at the listener again of 1,750. The velocity of sound is 340. 340. The listener is not moving, so there's a 0 on top. And we don't have the frequency of the source. Now it's moving away from you, so you have a positive at the bottom. And this is your second equation. Right. Would you be able to solve that simultaneously? Yes. The frequency of the source in both scenarios must be the same. So I'm going to make that the subject of both equations. So I'm converting this equation by just multiplying both sides with the inverse of that bracket. So that will give me 2,600. Multiply 340 minus Vs over 340. And that will leave the frequency of the sound at the other end of the equation. So that becomes my new number 1. I'm going to do the same here. I'm going to multiply the 1,750 with the inverse of that bracket. So it cancels on the right-hand side, and that will give me the frequency of the source. Now I can make those 2 equations equal because both frequency of the source will be the same. So 2,600, 340 minus Vs over 340 will equal 1,750, 340 plus Vs over 340. Right, you can write it down or photograph it in a minute, but I want to see if you can actually solve that equation. It's not nice. And this has become very popular. Because look, in the Doppler effect, there's only a bit of theory and a basic sum. Now, a basic sum everyone can do. It's not a challenge. You just pop in everything into the formula, and you remember if it's coming towards you, it's what?
It's negative.
And it go, yeah, I don't remember. I just work it out as I see the equation. If it goes away, it's positive. And then you just pop in the values and boom, boom, you got 3 or 4 marks. But now they make you solve 2 simultaneous equations or 2 equations simultaneously. Makes it harder. Just write that down. Just play around with it. See what you can do. Look, it's not difficult. Again, if you have a cool calculator, you can just, there's nothing you do. Just type in. I'm going to just type it in. And I'll show you now what is an easy way of doing it. It's important that you be able to do these calculations. And now my calculator is not going to like this. It's too much work. Because I think it runs through a table, putting all the possible values in. And that's why it takes so long. It's going to take, wow, okay, that was too quick. 66,44 meters per second. Let's see if this calculator is correct. 66,44 meters per second. That was way too quick. Sounds fine. Right, what I'm going to do, I'm just going to multiply with 340 right through. So it cancels there and there. Good. Then I got 2600, 340 minus VS equals 1750, 340 plus VS. Then I'm going to divide with 1750 right through. So it's just 2600 divided by 1750. And that gives me, well, it gives me 52 over 35. And then I have 340 minus VS equals 340 plus VS. So now I have to multiply that out. So that fraction, I'm going to multiply with 340. Then I get 505,142 minus 52 over 35 VS equals 340 plus VS. And then I'm going to subtract that 505,142 with 340. And I get 165,1428. And then I'm going to add 1 plus 52 over 35. Just typing correctly. Because I'm throwing it over to the other side. Then I get 2,4857 VS. So now 165.1428 divided by that 2.48. That gives me 66,46. I get 46 now because I rounded off earlier. VS is 66,46 meters per second. Okay, my silver calculator gave me that answer. It's more correct because it didn't do any rounding off. I have some rounding off here, which I should not have done. I should have put more decimals in or used a fraction. I don't know if you can see this. What I'll do is I'll just take this sum and stretch it out here. If you want to take a screenshot, you can do that. So the next chapter on reaction tempo, or the tempo of the reaction, is easy. This is a section of the chemistry that's not difficult. So you can work through it very quickly, actually. Can I continue?
I can ask a question. Is
obviously
when it comes to the Doppler effect, and what's this? Is this the hardest that it's gonna be?
Yeah. There are some other sums where you have, say, for instance, a bat chasing a moth or something, and then the then the problem with the question is it's asked, it's not properly formulated. So you can't really determine from the question what's happening. I mean, is the sound leaving the bat, because the bat is like making the sound, so it's the source and the list, and it's basically can be the listener. Do you understand?
Yeah.
Because the bat might be stationary, but the moth is moving away from the bat. So then the position of the bat might be both the source and the listener, and the velocity at which the moth moves away from it is the one that's at the bottom. But that's the problem with that question is it's so difficult to formulate. You can't really determine what's happening. So you have to draw a picture there. But this is the hardest it's going to be. It's not going to be harder. You can probably just suspect that you get a normal Doppler sum of just a vehicle moving away from a person or towards a person. All right, let's just test ourselves on that quickly. Not the bat, just a normal one. This is my house. You see, it's only got one door. And there's my alarm. Now, there was a guy trying to break into the house. And now he runs away. The alarm went off, and he's running away. Also, okay, so I want the frequency of the alarm is, say, for instance, 1,420 hertz. But as this guy is running away, he hears a frequency of let's say, 1,900 hertz. I want to know, what is the velocity the thief is running away? Yeah, it's running. What's his velocity? Okay, let's get that equation. Remember, there's a little part in your Doppler chapter that's also on light. It's called redshift. Just a little bit of theory, and you need to explain it. We can talk about that in a minute. Right. Quickly do this one. He's running in that direction, away from the house. Is it difficult? No, but you'll find that the source is now stationary. Obviously, the house is not running in the other direction. The source is stationary, and the listener is running or moving. Tell me if you have an answer.
Can I ask something?
Yes, obviously.
The speed of sound.
It's 340 meters per second. Look, it's not 340 exactly. It's 300 and what's it, 80 odd something, if I can remember correctly. But if they'll give you a value, the they should give you a value. I can't remember off by heart, but it's not 340. That's just a rounded value. But this wasn't your question, eh? Speed of sound is also, well, it depends. It depends also on temperature and stuff. It's 343. Okay, so let's do this. What is the frequency at the listener? It's 1900 hertz. Okay, 340, 340. Okay, the source is stationary, so I've got 0 at the bottom. I'm going to fill in 1420 at this at the frequency of the source. Now, I need to increase 140 to 1900. Therefore, I have to increase the top value. So I have to do a plus there. Are you with me, Kutso?
Yeah, I got that.
Okay, and that's just going to be VS or VL for listener.
Yeah.
Cool. So I'm dividing 1900 and with 1420. And then I'm multiplying up to 340. And then I'm subtracting 340. I'm just doing this calculation in my head, or as is. So that's impossible. Eh? Is that 114,93 meters per second?
I got the same answer.
Okay, this is not a thief anymore. That's like, I don't know. It's probably an alien ship or something. Because there is just no vehicle that can do 114 meters per second. Or person, in other words. Right. Okay, we are finished with this chapter. Let's just talk about red shift. Quickly, just what is it? Okay, so for instance, this is Earth. And we have like a huge telescope. And there's a distant galaxy. And it's got its own stars or suns. Now, okay, let's just move that because I can't draw that. It's too high. Come, why are you not moving? There we go. So that galaxy can either move towards us or move away from us. In general, everything is moving away from us. And why is that? Why is everything in the universe moving away from one another, not towards one another? Come, people, think.
Isn't it because of centrifugal force?
No. Say, for instance, I'm just going to waste 5 minutes of your time, if that's all right. Say, for instance, I have a hand grenade here. I don't know, it doesn't look like a hand grenade, but let's assume it's a hand grenade. What happens if it explodes? All the bits goes in what? Different direction. Is that right? It's called shrapnel. So, if all of these little shrapnel pieces is going in different directions after 2 seconds, say for instance we can rewind the time slowly, like in a millionth of a second at a time, what will all this shrapnel be doing? It will move back towards the grenade. Can you visualize that? So all the shrapnel will go out, and if you rewind the clock very slowly, all the shrapnel pieces comes together, and what do they make up? A grenade again. Can you all visualize that? No. Hello? Kutso,
Yes.
could you?
Yes.
Can you visualize that? No.
It was going in reverse.
Bernice, can you visualize that?
Yes.
Okay. So the reason why everything in the universe is moving away from one another is because right at the beginning, they were all together, like a grenade, and they exploded. So they're moving all away from one another. So what happens basically, the light that these stars give off, because they are moving very fast in one direction, they do exactly what that car did with the siren on top. They're catching their own light and leaving a trail behind. So the light waves would look like something like this. So the wavelengths behind the galaxy is larger than the wavelength in front of the galaxy. And that is called redshift. Now, how do they determine that? They take the sun's light. Here we have the sun, and they shine it through a spectrometer. And it gives you absorption spectrum and emission spectrum. In other words, each element, like magnesium, sodium, hydrogen, lithium, fluorine, nitrogen, each of those elements absorb a different frequency of light. So now you have like a strip here, and you have various areas. So for instance, that's the absorption spectrum of helium. And this is the absorption spectrum of, say, for instance, chlorine gas. Now they have all the different elements, like 10 or 15, they take 10 or 15 different elements. Then they take the light that comes off that distant galaxy and they compare it with the spectra here. And then you'll find that your chlorine bar will be somewhere there. And it would actually be blue or something. And your helium bar would be something like there. So they'll say, look, it shifted to the right. The chlorine shifted to the right. It shifted to the right. To the right of the spectrum is red, and to the left of the spectrum is blue. So by shifting it to the right, they can actually measure that distance that it shifted. And that distance is shifted, they can use with a Doppler equation, just a bit more complicated one. They can actually use that distance to determine the velocity at which that galaxy is moving away from us. Because that galaxy also has the same elements than our galaxy or our planet. That's a little bit of theory at the end of your Doppler. You just need to explain what is redshift. If a galaxy is moving away from you, the light will shift towards the red spectrum. If a galaxy or a star is moving towards you, it will shift towards the blue spectrum. That's called blue shift. It's just one mark in the exam, Max. Are you happy? Right.
Yes.
There's 10 minutes left. Do you want to do another work energy example, or you want to do another Doppler example?
Work energy.
Okay.
Okay, good. Oh, this is way too long. Okay, we'll make our own example. Right. Let's see. There's a slope and a box with a mass of 8 kilograms. And there's no friction here on the slope. So it's starting at a position called A, and the angle here is, let's say, 50 degrees, and it slides down to B. The height difference is 2,8 meters. It reaches B, and then there's friction here of, let's say, 12 newtons, and then it reaches C. So what happens? The box is at rest. It's got no velocity. So we hold it there, and then we leave the box. It slides down a frictionless surface towards B. When it hits B, it encounters friction, and it slows all the way down, and then the box stops at C again. Right. I just want you to tell me various ways how we can calculate the velocity at B. How can we calculate the velocity at B? Remember, there's one value missing. I didn't give you the distance of the slope. I just gave you the height. Think about it.
I think we can use V net.
Yes, you can use V net. It's true. You can use V net is the change in kinetic energy. And that's fine. I can do that. Explain to me why that would be a difficult route to take.
Because you would need, I think, what's the velocity?
No, you've got the no, you don't need the velocity. You want to work out the velocity.
Oh yeah, okay, then. But then
It's fine.
You
You
also-
can do that. The problem you have with VNet is that you don't have the distance between A and B, but you can use it. The easier equation to use is VNC, and that's the change in kinetic energy plus the change in potential energy. So normally what I do, if I get the height, then I use this equation. If I get the distance, then I use this equation. But in real life, you can use any one of the two. So this one will be easier, but let's use the harder one because you wanted to use that one. Right, so what is VNet? Look at my diagram of forces, my free body. So the net work is the work done by the parallel force. That's the only work parallel to the surface. And that will be the change in kinetic energy, which is half times the mass times the final velocity square minus the initial velocity square. So now what is difficult here? The work done by the parallel force is the parallel force, delta x, which we don't have, cos theta. And that is half times the mass times the end velocity, which we need to find, minus 0, which is the initial velocity. Okay, so what is FG parallel? That is mg sin 50 times x. We don't have x. Times cos 0 degrees. Why? The movement is down slope and the FG parallel is also down slope. That will be 4FV squared. Okay, mass 8. Gravitational acceleration 9,8. Now sin 50. Now you can, there's various ways of doing it. You can either look at sin 50 and say, look, I can calculate it. I could just keep sin 50 there. Why? Look at what happens if you calculate delta x. Now, sin of 50 equals opposite, which is 2,8 over hypotenuse, which is delta x. So instead of sin 50, I can write 2,8 over delta x. And then I multiply it with delta x again. So delta x is cancelling. But this is a quite difficult, if you haven't done an example, seeing how it cancels. Otherwise, you look at this equation and you think, look, I've got two unknowns. Really? How am I going to solve that? So that is why this equation sometimes works out better then, because you don't have that problem. You can work out the height very easy. Or you could have just worked out the height with that value, with normal trig. So now we have 8 times 2,8 times 9,8 divided by 4. And then we take the root of that answer. Oops. 7,41. The velocity is 7,41. So why am I writing a 4? It's 7. 7,41 meters per second. Okay. You don't know this chapter well enough, neither one of you, but don't worry about that. I can send you a couple of examples. You need to also find examples in exam papers and just practice this. This can be a lot of marks. Then you also have to learn about conservative and non-conservative forces. Right, look at this. Just want to show you one more thing and then we're finished. I'm going to redraw that drawing. We're going to leave the friction part for later. So I've got that 8 kg box again there. And the angle was 50 degrees. Was it? Yeah.
Yeah.
50 degrees. And I only had a height here of what? 2,8 meters now. Now, look at this. The work done by the parallel force, if there's no friction, we don't have any friction. Let me explain it this way before we do this. I've got a slope here, like a slide. You know those slides that we played on? There's two guys going to sit on, do this slide. One guy is going to slide down, and the other person is just going to jump down. If there's no friction, they're both going to hit the ground at exactly the same velocity. That slide can do this. If that guy slides down there with no friction, he's going to hit the ground at exactly the same velocity as if he've jumped down. So if it's 100 meters high, you might as well jump down, because you're going to hit the ground at the same velocity as if when you slide down, if there's no friction. But in real life, we know there's friction, so that's why you don't jump down, but slide down. Okay, so you could have worked out this. This is FG parallel delta X cos theta. That's the work done by the gravitational force parallel to the surface. So that is mg sin 50 times the distance, which is delta X. And we're going to just leave cos out because this is 1. So that's a mass times 9,8 times sin 50. And now we can work out the height if we want to. So sin 50 is 2,8 over delta X. So delta X is 2,8 over sin 50. So that's just 2,8 over sin 50. Now the sin 50 cancels. So that's just 8 times 9,8 times 2,5. But those two, the work done by the parallel force is the same as the work done by gravity. In other words, sliding down there or jumping down there, the work is exactly the same. Now, the work done by gravity is the gravitational force times the distance cos theta. Now, the gravitational force is mg. The distance you jump down is 2,8 cos 0 degrees, because if you jump down, the force is down and the movement is down. So now the mass of the person of the box is 8, the gravitation is 9,8, and the distance is 2,8. Exactly the same. So there's another way of skipping this difficult part. This part is just by using not FG parallel, but just using FG. And then not the distance. Then you don't use the distance of X. Then you use just the distance of the height, which is 2,8 meters. But I realize this can be a huge jump for you to do this now. Okay. But you must know this. So you can go and look at this video again. You must know this because your slope could have looked something like this. And there's the box. Now there's A and there's B. Now, how are you going to determine the velocity at B? You don't know that distance of A, B. There's just no way of calculating it. Well, then it's the same as jumping from A to C. If there's no friction. They won't give you friction on that slope, okay? It will be no friction. So the velocity at B would be exactly the same as the velocity as if you jump down directly from A to C. The work done by the parallel force will be exactly the same as you do the parallel section from A to B as if you've done directly from A to C. Okay, just remember if you get something that is difficult like that. Okay. I am planning, we must plan for the following. We try, I've got times on Monday as well, that's open at the moment. Nearer to the exam, we must maybe look if we can't fit in a Monday somewhere extra, just to do, and then I give you some examples to do, and just so they've got questions. Okay. Your workload is at least 2.5 chapters more than any other school would do, a normal cap school, okay? Your workload is too much. And I'm a little bit worried about that. Because if you were in school, you would have spent 2.5 weeks just on work and energy. All right. You've done it in less than a week. Cool. But I'm convinced that you can do well. All right. If you need anything, you can go on, just type in past physical science grade 12 past papers, and there's hundreds of them online where you can do Doppler sums, you can do work energy sums, you can do momentum impulse sums. Okay, similar with your chemistry. I'm going to say bye.
Right. Bye.
Thank you all. Bye-bye.
Bye.
Bye, Puna. Of Boena.
Bye.
Ek raak heeltyd in mekaar met jou.